Chapter 3, Section 1. Now that we have done the background work to see where the instantaneous rate of change comes from, we can derive formulas for derivatives that will make our work much easier. Keep in mind, though, that a derivative is just the slope of the tangent line at a point. Let's start with constant functions. We know that the graph of any constant function, y equals some number c, is going to be a horizontal line where y equals that number. Since a horizontal line has a slope of 0 everywhere, the derivative will also have a slope of 0 everywhere. So our first rule is going to be that if your function is just a constant, which is any number, 5, 7, 12, then the derivative will be 0. Next in line we have linear functions. So what if f of x equals mx plus b? Well, we know that if we draw a tangent line onto a linear function, it will lie on the line. This means it will have the same slope as the original line. Since the derivative is the slope of the tangent line, the derivative will just be m, which is the slope of the regular line. Let's look at some examples. If f of x equals 6, the derivative is 0. If f of x equals negative 15, the derivative is 0. If f of x equals 4x, it's no longer a constant, now it's a line, so the derivative will just be the slope of that line, which is 4. If f of x equals negative 10x, then the derivative is negative 10. If f of x equals 7x plus 3, it will still have a derivative that's equal to the slope of the line. The plus 3 is a constant that goes away, that just shifts the line, so the derivative is 7. If f of x equals 2x minus 1, then the derivative is 2. There's different powers of x, obviously, as the numbers go up, so we develop a rigorous formula to use these. Now, the formula was derived a long time ago and uses limits, which we don't do in this class. So if you'd like to know where it comes from, you can look in the addendum of the book. So here, using that formula, we can find the following derivatives. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the fourth is 4x cubed. And going on and so forth, there's a pattern that comes from these general derivatives that allows us to get a general formula. So the derivative of x to any power of n will be nx to the n minus 1. So what that means is that the power will come down out front, and then you'll subtract 1 from the power. Let's look at some examples of these. So if f of x equals x to the 10th, then the derivative will be 10x to the 9th. The power of 10 came down out front, and we subtracted 1 from the power to get the derivative. X to the 18th will be 18x to the 17th. X to the 24th will be 24x to the 23. X to the 150 will be 150x to the 149. These all work on the same pattern. You can do this with negatives and fractions, but you need to be very, very careful with your math. If you have x to the negative 50, again, the power comes down out front, negative 50x. Now the power is 1 less. Remember, we were subtracting 1 from the power. So negative 50 minus 1 is negative 51. So the derivative is negative 50x to the negative 51. Similarly, if you have x to the negative 3, negative 3 comes down out front, subtract 1 from the power, and you get negative 3x to the negative 4. Let's look at some fractions. If you have x to the 1/2, the 1/2 comes down out front, subtract 1 from the power, half minus 1 is negative half, so our derivative is 1/2 x to the negative half. X to the 1/7, if we want to find the derivative of that, the 1/7 comes down out front, and you get 1/7 x to the negative 6/7. You can also have a negative fraction. So here we have x to the negative 1/3. The negative 1/3 comes down out front. X, subtract 1 from the power, and you get negative 1/3 x to the negative 4/3. So if you have a constant that multiplies your function, so there's just a number in front of it, the constant will carry through. So what does that mean? If your function is 4x squared, then the derivative will be 4 times the derivative of x squared, which is 2x, and you can multiply those constants together to get 8x. So the way you want to look at this is that that constant carries through. So how I like to look at it is that the power comes down and multiplies the number out front, and then you also again subtract the number from the power. So when you have 7x to the fifth, the 5 will come down, multiply with the 7 to give you 35x, subtract 1 from the power to the fourth. So the derivative will be 35x to the fourth. Again, be very careful with fractions and negatives. If you have 6x to the 1/2, the 1/2 will come down out front and multiply with the 6 to give you 3. X, subtract 1 from the power to give you -1/2. If you have 9x to the -4, -4 will come down out front to multiply the 9, giving you -36. X to the -5. The sums and differences of functions. Well, if you have different functions added together or subtracted from each other, you can do them piece by piece. That's what this is saying. So if you have 2x cubed plus 4x squared minus 3x plus 7, since they're separated by addition and subtraction, you can do each piece separately. So the first one, 2x cubed, 3 comes down to multiply the 2, giving you 6, subtract 1 from the power, gives you squared, plus, and then the next term, we have a 4x squared. The 2 comes down to multiply the 4, giving you 8. X, subtract 1 from the power to give you 1. We generally don't write the 1, so we write that as 8x. And -3x, again, that's a line. We know the slope is 3, so we know the derivative is just -3. And then the 7 is a constant, and the derivative of a constant is 0. So let's go to the next example. We have x to the 6th minus 8x to the 1/4 plus 3x to the -2. So here again, we can go piece by piece because they're separated by addition and subtraction. So for the first part, we have x to the 6th. So 6 comes down, x, subtract 1 from the power, so you get 6x to the 5th. The next part, the 1/4 will come down to multiply the 8, giving you 2x, and now subtract 1 from 1/4 to give you -3/4. And then for the last piece, the -2 comes down, multiplies the 3, giving you -6x, subtract from the power to the -3. Let's look at a couple of tricky examples just so that you're prepared if you see something like this. If you have the square root of x, remember that that can be written as x to the 1/2. So if you want to take the derivative of the square root of x, first write it as x to the 1/2 and then do what we've been doing, where here the power comes down out front, 1/2 x, subtract 1 from the power, so to the -1/2. If f of x is 1 over x to the 4th, we can rewrite this as x to the -4. If you have a function where the variable is in the bottom raised to a power, and you don't want it in the bottom of a fraction, you can bring it up by making that power negative. So we can write this as x to the -4. Once we have it written that way, again we can apply our rules. The -4 comes down out front, x, subtract 1 from the power, giving you -4x to the -5. Obviously, it doesn't always have to be in terms of x's, sometimes it can be t's. So here we have 3t to the 1.3. So again, 1.3 will come down to multiply the 3, giving you 3.9t, subtract 1 from the power, so to the 0.3. One application that comes up is to find the equation of a tangent line. This comes up often enough that I'd like to do an example so that you know how to work this problem if it comes up again. Suppose that f of x is x squared plus 3x minus 4. Find the equation of the tangent line at the point x equals 1. So remember, the derivative is the slope of the tangent line. So what we need to find the equation of a line is a point and a slope. To get the point, you take the x value that they give you and plug it into the formula that they've given you to get the y value. So when you plug in 1, you get 1 squared, which is 1, plus 3 times 1 minus 4, which gives you 0. So now you have a point to work with, 1, 0. But we also need to know the slope of the tangent line. So the slope of the tangent line is the derivative. So to find the derivative, we use the rules we've just learned. The derivative of x squared, the 2 will come down, x to the 1, plus the derivative of 3x is just 3, and the derivative of -4 is 0. So f prime of x is going to be 2x plus 3. Now, we want to know at x equals 1, so we're going to plug the number in to get the slope at that point. So we plug in a 1, and we find the slope to be 5. So we know that the slope is 5, and we have a point that's on the line, which is 1, 0. So using the point and the slope, we can plug it into the y equals mx plus b form, solve for b, and now we know the equation of the tangent line will be y equals 5x minus 5. Now would be a good time to try the homework from Chapter 3, Section 1.